Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So we will be starting off with Dijkstra's algorithm in this video, and this is one of the most important algorithms if you're solving problems related to shortest path. Okay, now what does this algorithm state? The algorithm is very simple and straightforward. It states that you'll be given a source node. Assume over here I'm saying that the source node is 0. What does the source node means? The starting point. This is where you're going to start. So I'll be like, okay, the source node is 0. In order to reach 0, what will be the distance that you'll take? You'll be like 0. From 0 to 0, 0, right? But if I ask you from 0 to 1, what will be the distance that you'll take? Now, what is distance? From 0 to 1, you can go via various paths. You can travel directly. And if you travel directly, this is the edge weight that lies on that path. And that is what the weight of the path is. So I can say, if I travel directly from 0 to 1, the weight of the path will be 4. There can be multiple paths. One of the paths can be this, which travels via 2. And if it travels via 2, there is a 4 and there's a 2 line. And that will give a total path weight of 6, right? There can be other paths as well, where you decide that you're going to take an entire journey of the graph and then come. There'll be more 4 plus 3 plus 2 plus 3 plus 1 plus 2. But what I'm concerned about is to find the shortest one. So can I say the shortest one is 4, right? And if this would have been something like 1, can I say the shortest would have been then this path, which is 1 plus 2, 3, right? So the task is very simple. Given a source node, from that source node to every node, yes, to every node, you have to find the distance. So till 2, you have to find the distance. That will be something like again 4. Till 3, you have to find the distance. So what you need to do is you need to make sure from 0 to all the nodes, from 0 to 0, 1, 2, 3, 4, 5, 4. I should know what distance will I take as the shortest one, because I need the shortest one. That is what you need to tell me. And that is what the Dijkstra's algorithm will help us to find. Now, Dijkstra's algorithm can be implemented by 2 methods. One of them is actually 3, like you can go across to 3, but one is priority queue. The other one is the set. So you can use the data structure priority queue. You can use the data structure set as well. You can also use the queue, which is the third one, but this will take more time. Priority queue also takes a bit of time. Set is the fastest. So in this video, I'll be telling you the priority queue approach. Then in the next video, I'll be teaching you the set method, and I'll also be covering the intuition. I'll also be covering why priority queue, why not queue. I'll be covering all the questions that you will have in your mind when you go through this particular algorithm. So you don't need to worry. Just make sure each of the videos watch till the end. I've seen a lot of people skipping a lot of portions, but I do say a lot in between as well. So do not skip. Make sure whatever videos I make on Dijkstra's algorithm, watch them one by one. It can be 3 or 4, but make sure watch each and every video to get the concept clear. Because once the concept is clear, then we will move to solving problems. Yes, we will be solving a bunch of problems. And at the end of the day, you can solve any problem of Dijkstra's algorithm that comes in your interviews. We will be implementing the Dijkstra's algorithm using the priority queue. So the graph can be represented in an adjacency list. And this time we will be storing pairs. Okay, so something like if zero's adjacents are 1 and 2. So I store something like 1, 4, which is basically the node and the weight. The node and the weight of the edge. Something like 2, 4. The node and the weight. Node and weight will be stored. So this is how you can store the adjacency list. So if you're standing at 4 and if someone does ask you, what are the adjacent nodes of 4? You'll be like 2 and 5. What is the weight till 2? 1. What is the weight till 5? 3. This is how you can figure out from the adjacency list. So in order to implement this particular algorithm, there is an initial configuration that we will start off with. We will always have a mean heap data structure, and the mean heap data structure will always store a pair, a distance and a node. Remember this. What is a minimum heap data structure? So if you're storing anything in terms of distance and node, the shorter distance, I repeat, the shorter distance will be at the top, right? And if there are equal shorter distance, the earlier node or the shorter node will be at the top. You'll understand as we move. We will always have a distance array, which will keep track of how much distance are we taking in a path. Okay. And we will have the source node. And source node can be 0, can be 1, can be 2, can be anything. So as of now, the source node is 0. So the first step of the algorithm is very, very simple. What we do is we say rather that the source node is 0. So from 0 to 0, we are definitely sure that the distance will be 0. So we go and put a distance 0 in the distance array, and we say 0 distance, 0 node, and we put that into the minimum priority queue. That's the initial step 1. Now we start the iteration in the priority queue, and it's similar to BFS. We start the iteration, we take the topmost element in the priority queue. As of now, there's only one element, so we just take it out because that will be the topmost element. So we are saying we are taking a distance of 0 in order to reach node 0. We're taking that much of distance in order to reach node 0. So 0 says, hey, where can I go? 0 is like, I can go to 2 and I can go to 1. There are two ways in which you can proceed from 0, right? And how will you figure this 1 and 2? If you remember, adjacency list will tell you about that, right? So just figure the 1 and 2 from there. So I can actually move to something like node 1. And how much distance will I take? If this is taking plus 4, this is going to take 4. Why? Because previously I took 0. I'll take another 4, which will make me a distance of 4. Remember, previously you will be marking all these distance as infinite, a very big integer, which will mean that you never reached those nodes. So in order to reach node 1, you're taking a distance of 4. Can I say it's better than previous? It is. So go and just replace it with a node with a distance 4. Take the 4 and the node 1, put it into the priority queue. So I repeat, every time you get a distance which is better than the previous distance, that means you discovered a new path and you take that distance and put it into the priority queue always. Okay. What is the next thing? You can always go to the node 2, which is the next adjacent. If you carefully see, node 2 is the new adjacent, which you can go at a 4. So I can say another 4. So the new distance taken will be another 4. And 2 previously was infinite, 4. So 4 comma 2 is what I'll put into the priority queue. First iteration done. Similar to BFS. Next, who will be at the top of the minimum heap? Can I say 4 comma 1 will be at the top of the minimum heap? Why? 4 is equal in both of them, but 1 is smaller. Minimum heap. So 4 comma 1, yes. So I'm saying I'm taking a distance of 1 in order to reach the node. Distance of 4 in order to reach the node 1. Very obvious. From 1, where can you go? Again, you look at the adjacency list. It will say you can go to 0 and you can go to 2. Correct? So go to 0. So you can go to 0 and that will take a distance of 4, which will make it a total distance of 8. Will you consider this? No. Why? 0 is already reachable at 0 distance. Not to be considered. Where can you go? You can also go to the node 2 by taking a distance of 2. Why? From 1, if you go to 2, you take a distance of 2. Easily figured by the adjacency list. So plus 2 plus 4 takes a total distance of 6. Is it considerable? No. Why? Already reachable at 4. So no one was taken into consideration. Done. Let's get the next one. Only one guy out. Takes a distance of 4. Add a node 2. Where can node 2 go? Again, look at the adjacency list and you will see that 2 can go to 0, 2 can go to 3, 2 can go to 4, 2 can go to 5, 2 can go to 1. It can go to everyone. So I'll try to go at first to node 0, which is going to take me 4, which will make me a total distance of 8, not to be considered. I'll try to go to node 1, which will take me plus 2, which will make the total distance 6, not to be considered because we still have better alternatives. Next, I'll try to go to node 3, which will take me plus 3, which will make me the new distance 7. Understood? Previously took 4. From 2 to 3, 3. 4 plus 3, 7. 3 is infinite. Someone better. 7 better. So 7 comma 3. We got someone better. Next, I'll also try to go to node 4 by taking a distance of 1, which will make a total distance of 5. Again to be considered. 5 comma 4. Next, I'll try to go to node 5 by taking a distance of plus 6, which will make me a total distance of 8. Again, 4, 6, this 6. Distance 10, better than infinity, to be considered. So I'll take 10, comma 5, put it into the priority queue. So you got 3 guys that went into the priority queue. You got 2 guys that got discarded. So just omit this off. What's the next step? Who is the topmost element in the priority queue or minimum heap? Get it out. There's 5, there's 7, there's 10. The 5 comma 4 will be at the top. So 5 of a node 4. 5 at a node 4. Where can node 4 go? It can go to node 2 and it can also go to node 5. You can observe from 4 you can go to 2. You can go to 5. Easily figured out by the adjacency list. So from 4 to 2, distance of 1, 6. Not to be considered. From 4 to 5, 3. Distance of 8. Will you consider this? Yes. Because you got a better one. So 8 comma 5 will be considered. 8 comma 5 will be considered. Okay. Done. Perfect. What's the next thing? Next thing is who will be the next guy. So we have 7, we have 10, we have 8. 7 comma 3 will be the next guy. So distance of 7, node 3. So where can 3 go? Let's stand at 3 and see. 3 can go to 2. I think 3 can go to 5. 2 places. 2 and 5. So it will try to go to node 2. Take a distance of 3. Make a total distance of 10, which will not to be considered. It can go to 5 by taking a distance of 2, which will make the total distance of 9, not to be considered because we have 8. We have 8. Got it? So no new results. Omit this. Next, we'll take the next element out, which is, so 8 comma 5 is done by the way. Sorry, 7 comma 3 is done by the way. Next, you will take the next out, which is 8 comma 5. So distance of 8 to node 5. Where can 5 go? Where can 5 go? 5 can go to 2, 5 can go to 3, 5 can go to 4. So we'll try to go to 2 again with 6, which will make a total distance of 14, not to be considered. We will try to go to 3 with a distance of 2, which will make a distance of 10, not to be considered. It will try to go to 4. Yes, it will try to go to 4 with how much distance? It will try to go with 3, which will make it 11. 4 is better, not to be considered. Similarly, you will again take out 10 comma 5 this time. And again, you'll try out 3, 4, 2, and none of them will be considered. So apparently, we're done. Apparently, we're done. And once you're done, you will see this distance array stores the minimal. If you see till 5, it is saying 8, which is very much sensible. Why? Because if you carefully observe, yes, if you carefully observe, from 0, you can go to 2, which will take you a distance of 4. Then you can go to 1, then you can go here. So in this way, you can actually take 4 plus 5 plus 3, which is 8. All the other parts, even if you try to take this, it's going to cost you 9. So all the other parts will cost you more. So you got your minimum distance stored in your distance array. If you return this distance array, this is what your particular answer will be. So guys, I hope you have understood the algorithmic explanation of Dijkstra's algorithm. Now it's time to code it up. I'll be coding the C++ on the right, and you can figure out the exact similar Java code on the left if you have syntax issues. So it states the graph does not contain any negative weight cycle. Now remember, Dijkstra is not applicable to graphs with negative weight cycle. I'll be discussing that right after coding this up. Okay, so if you carefully see, we are given the number of nodes. We are also given the adjacency list and the source. So Usually it's a list of int. So we are given a vector of int. Why? Because we are storing a node, the adjacent node, and the weight as well. So instead of a pair, we are storing it in terms of a list. Okay. So what is the thing that we took? We took a minimum heap. This is how in C++ you declare a minimum heap. Then what is the next thing we did? We always had a distance array of same size. Done. And everything is, if you remember, marked as infinite. So make sure you mark everything as infinite. In our case, we can mark infinite as a very, very big value. Now, what is the initial configuration? We know that the source, from source to source, it is always 0. So we say, okay, from source to source, it is always 0. So we will do this. I'll say distance comma source is what the priority queue will have. Now we will iterate in the priority queue. Pretty simple. And we will be iterating in the priority queue. And what I'll say is, I'll get the top element. And in the top element, first I'll get the distance, right? What it has taken till now. And that will be stored at pq dot top dot first. And then I'll take the node, which will be pq dot top dot second. Once I've taken everything, I'll erase that element from the priority queue. Perfect. Now it's time to travel for the adjacent node. So this is how I'll travel. Now I know this auto of it this time is not an integer because it is storing two elements in form of a vector or a list. So I'll be like, okay, let me get the new edge weight, and it'll be very simple, it of 1 because it's stored at the second place. And can I say the adjacent node will be it of 0. Make sure in interviews you name the variables like this. Now, can I say if the current is this, like till reach the node you've taken this, and now you'll travel further adjacent weight. If that's lesser than what you will require, like what you have previously taken to reach adjacent node, can I say you got a better distance? And if you got a better distance, can I go across and say, okay, I got a better distance. Can you please update that for me? You'll be like, why not? And at the same time, can I say PQ, hey, you got someone better. Can you go across and store this distance? You'll be like, why not? Because you got someone better. So in this way, I can return this particular distance. This is how easy it was. So if you see the compilation is successful, now we will quickly submit it to check if it is working fine. So if you see all the test cases are running absolutely fine. Now you might have questions like, but Striver, why priority queue? What is the intuition? We'll be talking about all of these things in the next video. But in this video, I'll be telling you why a Dijkstra's algorithm will not work for negative weight cycle. So let's go and understand that. So Dijkstra doesn't work in any of the graphs that has a single negative weight. Okay. It also doesn't work if there's a cycle which ends up having a negative weight. So no negative cycles as well. So the whole reason lies around negative weight. It's a very simple reason. Just imagine I have a node 0 and I have a node 1. Okay. And I'm saying that, hey, listen, the distance, the edge weight is -2. So what do we initially do? We initially always take a priority queue, if you remember, right? That's what we do. We always take a minimum heap and we always take a distance array. In this case, the distance array will just be two people with 0 and 1, and we'll have a source, assume the source to be 0, and this will be infinity, right? And we'll put something like 0, comma 0, correct? And how do you solve this? You get this first guy and you say, okay, distance 0 to node 0. And a 0 says, I can go to 1, which is very obvious. You can go to 1 by taking a -2. So the updated distance will be -2. So apparently this will be updated to -2. -2, comma 1 is what goes into the priority queue, right? And then what I'll do is, I'll omit this, right? And next, I'll get this next guy, which says, I'm going to take -2 in order to reach node 1. Now node 1 says, I can go to node 0, correct? And how much it will take? A -2 again. So what will be the net distance? -4, which is better than 0. So -4. So -4, comma, node 0. Okay, perfect, done. So if I go again, and I take the next guy again, -4, node 0. If I try to go to node 1, I'll again take -2, which will make the distance to be minus 6. It keeps on going because on every traversal, the distance reduces. The distance reduces because of negative weights. So it's not costing you anything. It's just decreasing. So you can just keep on going forever, forever. That's why any graph with negative weights cannot implement Dijkstra's algorithm because it will fall in an infinite loop. I repeat, it will fall in an infinite loop. For negative weights, it's practically impossible because what do we mean by shortest path? I'm actually consuming something to go somewhere. Okay. If someone gives me something for going somewhere, I'm just gonna go every now and then, isn't it? I just keep on going infinitely because I'm gonna get it. I'm gonna get it. So I have to give something. I have to give a positive weight. That's how the paths are computed, right? That is why the Dijkstra's algorithm is only applicable for graphs with positive weights. So what about the time complexity of this particular algorithm? It's nothing but E log V, where E is the total number of edges in the entire graph. V is the number of nodes. There is a very, very critical derivation of this, which I'll be doing in the next video. I'll also be discussing why a priority queue is used, or why a data structure where you need the minimum at first is used, because in the same code, try this out, in the same code, replace priority queue with a queue data structure. It will still give you correct answers. Okay, it will still give you correct answer. You can try that out. So, but I'll be explicitly explaining these couple of things in the next video. And in another video, we'll also be implementing the same algorithm using the set data structure. And why are we going to use set data structure? I'm also going to discuss about that in that particular video. For this video, I think this is more than enough. And I hope you've understood the entire algorithm and the priority queue implementation, because this is where the base starts. And the next videos we will be elongating the other things. So guys, I hope you have enjoyed this particular video. Just in case you did, please make sure you like this video. And if you're new to our channel, what are you waiting for? I think you should definitely subscribe to us. If you haven't checked out our DP series and the SD sheet, the links are in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye-bye. Take care.